M. Rekha is there in the field. She's there? Okay, so M. Rekha is asking the question, how to determine the energy level? Why not use phosphorescence from triplet states? And she's also asking the question, how to determine the energy of HOMO LUMO of all the components. So this is something, a very good question, I would rather say. That's because there are different techniques where people measure HOMO LUMO. One of the technique is cyclic voltammetry. People do it, but again, one has to be very careful. And when you use cyclic voltammetry as an experimental method to determine HOMO LUMO, but there are recently people are using UPS, some complementary methods where you can get an optical band gap. One of the way of looking at the band gap. You can also look at CV, and if many more additional experiment, it is good for to accurately report HOMO LUMO. Otherwise, you see that for same material, I see the papers literature is flooded with all erroneous values. So here you have to be very careful when you do a experiment in the lab. Even the cyclic voltammetry experiment in the laboratory has to be done very, very carefully. So what I can say is you can use cyclic voltammetry is one of the method, but it will be always good to use other complementary methods for HOMO LUMO determinations. I hope I answer. Okay, DD is asking me this question. Does TADF requires lowering of the energy difference between the triplet and the singlet? How is that achieved? Is it by separating the electron and holes spatially? But that will also lower the recombination by affecting the oscillator strength. How do I avoid this? So this is the very, very important question. So this is something a TADF material is currently suffering. So so what we do with DD is we use a donor and acceptor, and we use some sort of a bridge to minimize the coupling between donor and acceptor. But as you rightly pointed out, that certainly affect the oscillator strength of the emission. So oscillator strength of a emission spectra is a major problem because the emission comes from the charge transfer states. So this is something at the moment I don't have any answer. How are you going to do that? But the only way of reducing the exchange energy is by using donor acceptor. So, but indeed, that's a major problem in TADF, where oscillator emission strengths are very, very low. So until unless you address this question, this TADF materials are not going to be very exciting materials for light emission applications. So that's my answer for DD's question. Okay. Okay, so King Shuk Dev Sharma from IIT Madras. His question is molecular design strategy to fabricate red apart from, okay, so red is something which is people have achieved. Red is 2 EV. Red is something which is, there are many chromophores people have achieved a red color, but blue has been challenging as I indicated in my lecture, because there you need to have a very wide bandgap semiconductor. So for red, low around a 2 electron volt, people already have many chromophores, which shows a good EQE, external quantum efficiency for the red. So going further, so I'm looking at, I think Rekha has many questions. How can you classify organic semiconductor as P-type? And so the other question is, how can we classify organic semiconductor as P-type and N-type? Yes, this is something, a hole carrier and electron carrier, where, a conventional semiconductor language, people use it for saying hole. So similarly here, it depends upon what kind of, there are materials also ambipolar. They can carry both hole and electron. So it depends upon mainly a device strategy. If you have a hole carrier material, what kind of, doping you do. If you suppose you are building a transistors and you inject the hole and you have a very high hole carrier mobility, then it's called P-type, and otherwise the N-type. So, okay, Ram Kumar, okay, from CNRS. Thanks a lot for presenting this wonderful and exciting talk. Okay, symmetric, asymmetric structure. Okay, does it really depend on the blends we wish to use the active layer? So this is some, it is this donor acceptor pi conjugated systems are covalently bound here. So they are not physically mixed. So the idea of donor acceptor is, in the context of solar cells, you reduce the band gap and make use of and tune the band gap. And for the TADF case, you can also reduce the exchange energy. So this is Ram Kumar's questions. Ram Kumar asked 2 questions. So Anand Pandey is asking, he would like to fabricate organic silicon tandem solar cells. What are the real challenges? Yes, there are many challenges. First of all, you need to work out the interface, the interlayer, how you are going to, make, suppose if you simply coat a organic layer on silicon, you will have a lot of interface defects. So it is important to really first look at this interlayer. So it is very, very challenging to optimize the interlayer between silicon and organic, and that is still a open challenge. And there are many researchers working in this area to build the tandem solar cells. Okay, Sangeeta. Okay, thank you. Okay, so Saumadeep Mitra is asking, okay, what should be the approach to make a less humidity sensitive organic solar cell, which has a tendency to get oxidized? So that is depend upon, again, if one of the approach is your position of a homo lumo. If the material, we have to really play with the energetics. If you expose to the moisture, some of the materials, it is depends upon where your homo is localized. So if you avoid a oxidation reactions with the organic semiconductor, then certainly you can make slightly better semiconductor. But there is no per se, sort of, when you shine the light, especially this high energy photon, and exposed to the, humid environment, indeed there is a degradation. So it's an effect of 2, light as well as humidity. So if together, you really cannot really, if you expose to the organic semiconductor, indeed they undergo a degradation. But the energy levels, one has to play with, again, very carefully with the energy level. So what is the highest efficiency for organic solar cells? So far, people have achieved up to 18%. There's a recent report in June where people have achieved 18% efficiency by using the bulk heterojection concept. By using non-fullerene acceptor and a P-type semiconductor, polymer semiconductor, 18% efficiency has been achieved. So single molecules or polymers, which gives a better efficiency for OLEDs. So efficiency it's a collective parameter. There are several aspects in efficiency. As I said, you have to take care of not only the pi conjugation, you have to also look at the singlet triplet ratios. You have to also look at, quantum yield. So there are in multifold parameter which influence the external quantum efficiency. It's not dependent upon a single parameter. Okay, but how? Yeah, I think I have answered most of the questions. I have not answered all of them because there are too many questions here. I just looked at. Okay.
Okay.
Ajay, do you have still time, or what should I like? There are
if you want to take up the last 2-3 questions, please go ahead, Professor.
Yeah. Okay. So, okay. Okay. Is there any limit for efficiency? Yes. Every solar cell has a limit for the efficiency. I talked about Shockley Pfizer. It is band gap dependent. And what are the losses here? In organic solar cells, we use different kinds of materials. So it depends upon the kind of material. You can always have an efficiency limit. If you really want to go beyond Shockley Pfizer, then you have to use the issues like a new ideas, concepts like singlet fission and other. So essentially, there is a indeed limit for efficiency of organic solar cells. Okay. So Sudhir is asking, is there any role of UV visible data helps in efficiency of organic IPS? Then how? So initially UV, the optical property of an organic semiconductor is a very suggestive. when you conduct this experiment in your lab, it will tell you many things. First of all, you can determine a extinction coefficient of a dye. You can also determine the optical band gap. So you know where the semiconductor absorbs which part of the spectrum. So a simple UV experiment is good to have begin, but that need not necessarily tells you what kind of efficiency you are going to get it. But this is a very, when you make any new semiconductor in your lab or organic material in your lab, it is good idea to always collect the UV visible data. There you see that optical band gap as well as extinction coefficient. You can calculate these parameters, and then you can further proceed to make a thin film.